Okay, so good evening everyone. This course is Advanced Machining Process, which is instructed by Professor Manas Das, and I am Chinmoy Datta, PMRF scholar from IIT Madras. So this week, that live interaction session will be on electrochemical machining. Maybe you have gone through the uh, lecture series, so I'll be briefly telling about the working principle and the construction of and the parts and working of this machine. So that chemical machining obviously is a like non-traditional machining process. Actually it belongs to that electrochemical category. So like is it's actually opposite to that electrochemical or galvanic coating or deposition process. So we'll be coming into that in later. We'll see that how this whole machining process will work. Okay, so that like is machine actually used to remove the metal and alloys like which are difficult to machine by mechanical machining processes, which we have seen in previous lectures, like ultrasonic machining process or pressive water jet machining process. Those materials, difficult to machine materials which are difficult to machine by those mechanical process machining process, those materials can be machined by electrochemical machining process. Okay, so that machining process actually we'll see in later like slides that it will be following Faraday's first law, second law. We'll see that how that laws will be occurred. Okay. So later we'll see that the what are the Faraday's law and how it is like machining principle actually follows this Faraday's law to remove the material from workpiece. And like material removal actually it happens in this like machining process is like atomic dissolution of material in the electrolyte. So we'll be seeing like in detail that what are the factors here working, and then actually what it requires to machine the like materials. It needs like from the figure itself you can see, so like it has two electrodes, an electrolyte, a gap that is between like tool and the workpiece, and a source of DC power supply. We'll be seeing like how it works, and then like comes to the application part on of that chemical machining process. Actually it's hugely used in the production of turbine blades in aerospace industries, in automotive industries for the production of turbocharger, trepanning process or drilling process. Also we can see that it's hugely used, that electrochemical machining process. So that process, like how it works actually. So actually while electrochemical machining process, there like will be some reactions occurring at the electrodes. So a few react okay. So if we see the working principle, firstly like here some reactions, chemical reactions will be occurring at the electrodes. That is like anode here is the workpiece. So workpiece is acting as anode and the tool is working as cathode. Okay, within that electrolyte we can see that yellow color, that is workpiece is acting as anode, and that is red color, that is tool is acting as a cathode. Okay, in that electrolytic solution. Okay, so like that like we, if we take an example, say for machining of that say for example we want to machine low carbon steel. Okay, so actually which low carbon steel, that means like it's a primarily like a ferrous alloy. Okay, so actually so that steel, low carbon steel, we can say this is actually made up of like it's made up of iron. Okay, just a minute, just a minute, hold on, like I'm getting some call. Hello, 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 Anna, where are you, Anna? Anna, I'm not there now, like after 45 minutes only I'm coming. Okay. Sorry for like delaying. So just a minute. Yeah. So, like here's we are seeing like that workpiece and tool are acting as anode and cathode, and like if we take an example of low carbon steel machining process, so low carbon steel actually is made up of ferrous alloy, that is iron. Okay, that so for that electrochemical machining of that steel, actually that alloy mainly like natural salt solution or sodium carbon like chloride solution is like we can say as an electrolyte. Okay. So like that solution of sodium like chloride or NaCl, if we take as electrolyte solution, electrolytic solution, then that electrolyte and water actually goes under some ionic dissolution or some chemical reactions. Okay, say for example, if we write those dissolution here, like, so actually NaCl will be Na plus Cl minus, okay, and H2O will be H plus OH minus, okay. So as like that potential difference is like actually applied between that workpiece, that is anode, and the tool, that is cathode, okay. Here like anode and like that. Okay, so that positive ions actually move towards the tool and the negative ion actually move towards the workpiece. So what happens here, like when that potential difference actually is applied between the workpiece and the tool, that positive ions moves towards the tool and the negative ion move towards the workpiece. Okay, so in this way actually hydrogen ion from that H2O will take away electrons from the cathode or tool, we can say, and form hydrogen gas. What it's like, the reaction will be then 2H plus 2 electron equals to H2. It will be at cathode. Okay, so it will form as a hydrogen gas. Similarly, that iron atom is there, right? Fe from the workpiece, like that, it contains of iron itself basically. So that Fe like atom will come out of the anode, that is from workpiece it will come out, that is Fe will be then Fe plus 2 electron minus. Okay, hello, yeah. Okay, if anyone is having any question, you can put it in chat box maybe, if you are not telling it, like I will try to answer it later even when we'll be seeing. Okay, so then like that cathodic and anodic reactions which we have seen, right, that within that electrolyte iron ions actually it combined with that chloride ions. So and like that, like sodium ions will be combining with hydroxyl ions to form that sodium hydroxide, or we can say that Na plus OH minus will form NaOH. Okay, so actually what happens, like FeCl2 and FeOH2 would form, like but it's actually in form of sludge only it will form. Okay, so it like it's that's what, like while machining it's noted that the workpiece gets actually gradually machined and gets precipitated as the sludge. Okay, so and that hydrogen gas which forms actually it evolves at the tool or that cathode which we have seen in the red color form. So that is the, in this way only that electrochemical reactions occur, and that material removal takes place gradually at atomic level dissolution, we can say, we have seen in the reactions. Okay, so that's what, like that we can get an excellent surface finish from this machining process. See, we can see that initial stage of the TCM and then steady stage of the TCM process when electrolytes are getting exchanged, and we can see the chemical reactions happen. Okay, so actually that voltage here is required like to be that applied for that electrochemical reaction at steady state only. Okay, so that steady state condition only, that voltage is applied, and voltage or potential difference which is around like it usually it's in between a range, actually 2 volt to 30 volt, it's in a range, so you can give that potential difference to that system, and that applied potential difference actually that overcome some resistance or potential drops, that is electrode potential or say ohmic potential drop or concentration over potential drop, ohmic resistance of that potential drop. So sorry. So this is how actually it works. Now, if we tell about Faraday's principle, maybe you have studied in like earlier that Faraday's laws of electrolysis. So that laws actually tells us that the weight of the substance produced during that electrolysis process is directly proportional to the current which passes, that length of time of process, and then equivalent to a weight of material. Okay, so what are the process like that electrolysis process, that is directly proportional to the current which passed, and then the length of time of process, and then equivalent weight of the material. We'll see in material removal process that how all the laws or all the states of Faraday's principle it's actually following. Okay, so two dissimilar metals actually are in contact with an electrolyte, and anodes loses metal to cathode. So in this way actually Faraday's principle works. Okay, so here we have seen that workpiece is working as anode, tool is working as cathode, and electrolyte which is actually electrically conductive field. That's all, right? So like here you have to remember some process parameters, like I have seen like I have said now, like voltage range will be 2 to 30 or 35 volt, current and current density, electrolytic temperature, flow rate, electrolyte dilution, and feed rate. Those are the process parameters which we have to keep in mind in while machining. And then the coming to the material removal mechanism of that electrolytic machining process. Okay, so here we'll see some equations and some derivations. So actually material removal rate, like material removal in ECM process takes place due to atomic dissolution, which I have explained in previous slide, that atomic dissolution of work material. Okay, that electrochemical dissolution actually is maintained by Faraday's laws itself. So the Faraday's first law, which states like that amount of electrochemical dissolution or deposition is proportional to the amount of charge pass through that electrochemical cell. Okay, so we can write it as M directly proportional to Q. Okay, so M which is directly proportional to Q, or like that M is the mass of, we can say mass of material dissolved, and Q is the amount of charge passed. Okay, so that this is according to the Faraday's laws, it is directly proportional, M directly proportional to Q. Okay, and then comes to the second law of Faraday's principle, which states that amount of material deposited or dissolved further depends on electrochemical equivalence of material, that is the ratio of atomic weight and valency. We have seen in chemistries also, like we have studied it, like that electrochemical equivalence is the ratio of atomic weight and valency of that like atom. Okay, that is M is proportional to ECE, we can write as electrochemical equivalence. Okay, which is nothing but a ratio of atomic weight to valency V. Okay, so like by combining both of the laws, we can write it as M is proportional to Q into A by V, isn't it? So that where like, or if we like F is the Farad, like if we can write it in such a way like that, F equals to FQA divided by V. Okay, F is Faraday's constant, which is 96,500 coulomb. Those will be very much useful if you solve any numericals using this machining process, or if you say calculate material removal rate, how much material will be removed if you do machining using that electrochemical machining process. So you have to like remember all those derivation. Okay, so that M we can write it as M equals to I into T into A divided by F into V. So like that I is the current and like rho is like, we can like further derive is as M by that MRR equals to, we can write it as T into rho, that is IA divided by F into rho into V. So where I is current and rho is the density of material. Okay, so that like materials are quite like often actually alloys, because we have seen that low carbon steel, which is also alloy, right? So whenever we'll machine some alloy, that atomic weights we have to, just a minute. So whenever like calculating this MRR and that derivation, we have to keep in mind that that alloy is like combination of some materials, right? So we have to keep in mind that atomic weight of every material, like say as atomic weights as A1, A2, and in such a way we can write it as F1, from starting from A1 to A1, those atomic weight. And if we say that valencies are V1 to Vn, okay, so that for passing the like I current at a time t, the mass material, like mass of that material dissolved will be then m equals to mi equals to delta t a rho into a, okay, that is alpha. Okay, so that delta a is, it is denoted as total volume of alloy. Okay, total volume of alloy, and like each element actually present in that alloy takes a certain amount of charge or dissolve, charge to dissolve, right? So we have to keep in mind every material's condition, that is atomic weight, valency number, that is total volume it is used to dissolve, those density of material, those all those things we have to keep in mind. So if we like consider this, where shall I write? Okay, if we write it here, so Mi will be QIAI into Vi. Okay, so Q will be FMVI divided by AI. That is, Q is total charge passed. Okay. So A we'll know from the atomic weight like of that particular atom, B also valency, and then mass, and that F will be the Faraday's constant or like Coulomb, 96500 Coulomb. In this way we'll get Q. Okay, so then if we simplify the equation, then we'll get MRR. That MRR will be divided by T, that is 1 by F into rho 1 by summation of alpha I Vi by Ai. That is, if we say two atoms are there in that alloy, like two materials are there in alloy, so alpha I, summation of alpha I into Vi divided by Ai will be that like here, and multiplied by 1 by F into rho is the density of material. Those will be combining as MRR. So we'll get in such a way material removal rate. Okay. So like we need to like know the dynamics of that electrochemical machining process as well here. So here one question, previous slide one question is given as MRR in electrochemical machining depends on hardness of work material, atomic weight of work material, thermal conductivity of work material, ductility of work material. So from the equation itself we can say alpha I into Vi divided by Ai is there. So Ai is atomic weight of that work material. So MRR is like directly dependent on that atomic weight of work material. So we can say MRR in ECM depends on atomic weight of that work material. From the equation itself we can get the relations between MRR and other process parameters. Okay, so this will be the right answer. And here if we comes to the dynamics of that electrochemical machining, actually is that electrochemical machining actually can be taken place as without any feed to the tool, or even by giving a feed to the tool also it can be machined. Okay, so actually a steady machining gap is maintained in that machining process. So that dynamics then we need to understand between that job and tool, and then in the electrolytic place, and by giving a potential difference we need to understand how it works and how that what is the dynamics behind that machining process. Okay, so like say if it's a electrolyte, if we refer previous figures, and say for example this is job or workpiece, and this is the tool. Okay, so DH will come later to DH, and this is the distance is called H. Okay, this is the potential difference which is occurred between tool and workpiece. Okay, so if we see this like that over a small time period dt, like actually that current of I is passed through that electrolyte, and it actually occurs the electrochemical dissolution of the material of amount dH, okay, over the area of that S. So we can write it as I equals to V by R, or V divided by RH by S, that is Vs by RH. Okay. So why I am writing this, this is useful to find some derivation or calculation. Then dH by dt we can actually write it as 1 by F into Ax, or A divided by rho into V by RH into 1 by S. Okay. So from this, like if we derive that, we'll get see that constant which we will assume that, or like dH by dt will, like for given, it is actually potential difference we need to find. So for a given potential difference in alloy, the dH by dt will be C by H. C you can assume as a constant. Okay, then that C we need to find like V by F rho into summation of F rho R into summation of alpha I Vi by A. So if we put some initial condition, like from the graph itself we can say, if we put some initial condition like at t equals to 0, h equals to h0, and at t equals to t1 and h equals to h1, we can write it as integration h0 to h1 h dh equals to c of integration 0 to t dt. Okay. So If we integrate this, then we can get h1 square minus h2 square equals to 2ct. So why we are finding this, like from the diagram itself, as like tool and workpiece gap under 0 feet condition grows gradually from like by following a parabolic curve. We can see from the graph itself, like tool and workpiece gap under 0, if we don't give any feed to the tool, then that gap between the tool and workpiece, that is inter-electrode gap, will be like will be growing gradually by following a parabolic path as like shown in this figure. Okay, so and like as dH by dt equals to C by H, we have like we have told in that equations, then like we can say that dissolution would actually gradually decrease with increase in that gap. You have to remember those connection or relation between those things. See that tool workpiece gap will grow gradually in 0 feet condition, but the dissolution actually gradually decrease with increase in gap as the potential drop like across that electrolyte or electrolytic solution actually will increase. So as that potential drop between that electrolytic solution will increase, then that actually that dissolution will be decreasing with that increasing in the gap between tool and workpiece. Okay, so here one question is given as that inter-electrode gap during ECM is greater than 1 mm. Is it true or false? Actually that inter-electrode gap should be in ECM process should be less than 1 mm. It should be less than 1 mm. Okay, so it will be false. If you check the like requirements of that, then you can see that inter-electrode gap should be less than 1 mm. Okay, and one question is given as smaller inter-electrode gap results in higher MRR, lower MRR, and doesn't affect the MRR. Okay, so it is the right answer is the higher MRR. Okay, because that smaller inter-electrode gap will result in the density of that material, and then it will go, like MR material removal rate will be more, and that surface finishing also will be more. So this question, the right answer is high MRR. Okay, so let us see like one numerical. So in electrochemical machining process of pure iron, a material removal rate of 500 mm cube per minute is required. Estimate that current requirement. Okay. So what is given as material removal rate is MRR is given as 500 millimeter cube per minute. Okay. So from the derivation we have seen MRR is that is A into I divided by F into V. Okay, or and by rho T also you can write. Okay, so one relation we can get AI by FP, and one relation we can get M by rho into T. So both, if we say this equals to AI divided by FP, we can write, right? Okay, F into V into rho will be there, right? So this is MRR. So AI by FV into rho. Okay. So MRR is given as 500 millimeter cube per minute, but I guess we have to convert it into second, like 500 divided by 60 millimeter cube per second. If we convert it into millimeter per cube per second, what will be the result for this MRR? 50 by 6. right? So if we divide that 50 by 6, how much we can get? It's approx 8.3. Is it correct?
Yes.
Okay. So we are getting 8.3 centimeter cube per second. Okay. Okay. So actually, this F we need, right? That F is 96500 coulomb. That is in SI unit. So we need to convert it into, again that centimeter cube is there. So that we think we can write it as 8.3 into 10 to the power minus 3 for conversion. Okay. So that 8.3 into 10 to the power minus 3, if we write AI, A A will be like pure iron is given, okay? That atomic weight of iron is 56. So certainly actually you have to remember some of the materials, some of the atoms like atomic weight, or like generally even like if it's like large, like 2 3 numbers of atoms are given or alloys are given in a question, then they actually provide those atomic values. So generally that iron is very common, so we know that atomic weight of that iron is 56. So we can write A as 56. Then I we need to actually find out current, right? Then divided by F is 96500 into V. Okay. So it's, I guess that valency is 7.8, sorry, 2. That V is 7.2, okay. And that rho density of material is 7.8 gram per cc. So this is the those values actually, F, then valency of atomic, like that iron atom, this is 2, and that rho density is 7.8 gram per cc. Those things you actually have to remember for certain atoms or alloys. So if you calculate this value, what will be I will be 8.3 into 10 to the power minus 3 into 96500 into 2 into 7.8 divided by 56. So, okay, 96500 into 2 into 7.8 divided by 56 divided by 1000. What is the result of this I? What will be the current? It will be like coming in ampere only, like I'm getting 224, approx 224. Is this correct? You can also please calculate and let me know, like,
Yes, ma'am, correct.
okay, fine. So in this way, if I even say like other problems also given as that MRR equations, then if I and atomic weight and all those values are given, what will be the material weight? Using this calculation, you can see or you can explain like what will be the values of those problems. Okay, here like one more thing is there in that previous slide where the dynamics in the electrolyte, actually I forgot to mention. So here let's say that like initial gap is like dH by dt, C by H we have, but that like that irrespective of that initial gap also we need to find out H dash, or like say H dash, we can say it's H by H star, or it is equals to 1, that is FH by C equals to 1, or H equals to C by F. Actually thing is that like ECM actually is self-regulating, as MRR is like we will see from that derivation. Actually the aim of that derivation is to prove that the MRR is will be equals to that feed rate. So it's a self-regulating process that ECM is. So for that actually the derivation came that H equals to C by F, then or F equals to C by H, that is C we know that A V by F into rho V R into 1 by H. Okay, so that if we derive this F or simplify it, then we'll go get A by F into rho into V into 1 by S, or that is in MRR, that in mm per second. Okay, so from these like it has been like marked or denoted like that ECM is a self-regulating process, as MRR equals to that feed rate. Okay, because in previous slide we also proved that same equation itself. So from these only they have stated that it will be equal to that feed rate. Okay, so another question is electrolytes electrical conductivity value increases due to temperature, size of hydrogen gas bubbles and none. Okay, here if we draw one figure, that is y and x, so it's like, okay, this is y0, this is work material, and this is u0, y, u, and this is j. Okay, so from that only like you can get that the temperature actually increases that h. Okay, or like say, sorry, that h I've mistakenly I've said like h, no, not h, k, that electrical conductivity. Okay, electrolytes electrical conductivity, it's denoted as k, conductivity. So if it's denoted as k, actually temperature increases this value, that value, but that hydrogen gas bubbles actually decreases that value. Okay, from the figure itself it's denoted that gaps actually get tapered. Okay, so that internal electrode gap is there, right? So inter electrode gap varies along that electrolytic flow direction. Okay, so actually that gap increases, that means that current density actually decreases, sorry. So current density decreases means that the machining rate will be also decreasing. That means machining rate decreasing, that means that material removal rate also will be decreasing. So that inter electrode gap actually plays an important role in machining of ECM process, as if we increase that inter electrode gap, then that current density will be decreasing, and that current density will be decreasing means that machining rate will be decreasing, and that means that MRR will be also decreasing. In such a manner, like even that electrolytics electrical conductivity also plays a role, because it actually increases while increases due to that, like it increases k value, that electrical conductivity value, temperature actually increases, and then hydraulic gas bubble also decreases that K value. So both of the effect, temperature and that size of hydrogen gas bubbles, both together affect that electrolytes electrical conductivity. Okay, so that are the few of the questions and derivation I have prepared, like to give a brief idea on this. So anyone having any doubt?
No, ma'am.
Okay, so shall we close the meeting?
Okay, ma'am. Thank you.
Yeah,
Yes,
thank
ma'am.
you. Thank you.
Thank you, ma'am.